Hello. We will start today's lecture by recalling one unfinished business from the previous one. We have a system of linear equations, and this system has a precise solution because we assume that the matrix A is regular, so there is just one unique solution. But instead of finding it, which would be nice, we have to use some numerical methods, and it provides us with a candidate for solution. And we are not sure whether this vector that we found is actually equal to the solution. Most likely not. And then we would like to know how far it is from the actual solution. In other words, we are interested in the absolute error. And the absolute error is defined as the difference between the precise answer and the approximate answer. So our target is to somehow get information about the absolute error of our quotation marks solution. Now, what we did last time, we introduced the notion of residual, which is something like checking whether our solution is correct or not. We find that it's not. But now the magnitude of the residual is somehow telling us, hopefully, something about the precision of our solution because they are connected. And last time we deduced an interesting equality that the residual is A times the error. Or, if you want, the error is A inverse times the residual. So these are the two key formulas that we want to know, that we want to work with. And the question is, how does information carry over from one side to the other? Because we know the residual, we calculated it. So that's a vector that we know, we can play with it, analyze it. What does it tell us about the error vector? Can we, for instance, hope that if the residual is small, then also the absolute error of our solution is also small? That's a good question. Let's try an experiment. So, let's have a look here. I have a matrix 4 by 4. And just to show that things can be, let's say, interesting, even for nice matrices, this one is symmetric. This is not really crucial or important for our application, for our example, but it shows that even symmetric matrices may have interesting kinds of behaviors. Then we have a vector of right-hand sides, B. So we have a system of 4 linear equations with 4 unknowns, and have a vector X, which I think might be a solution, or perhaps close to the solution. I don't know how I got it actually. It's just a vector, candidate. So I calculated residual. You can see it in the upper left row over here. This is the residual code, B minus AX. And I obtained the vector R, which you can see over here. That's vector R. Now, I can see some reasonably small numbers. So this tells me that this vector X, which I guessed somehow, doesn't do really a bad job of being a solution. AX is not too far from B. I'm trying to reach B with AX. This is my target, and this is the way I'm shooting to it. So when I'm asking by how much I missed, we would actually prefer to see a relative error, of course, because we know that relative error is a much better indication of the quality of our result. So what I did, I looked at the individual errors, because these are really errors of each coordinate when I look at the vector R. So I took the individual numbers in the residual vector and divided them by corresponding numbers in the right-hand side B. And this tells me the relative error of each of the entries in the vector B in the right-hand sides, by how much I missed, but as percentages if you want. And the largest of these 4 numbers is 0.001, which is almost like 0.1%. So, in other words, it's roughly 10 to negative 3. That's the relative error in reaching the right-hand side of my system. Okay? So it seems I did not miss it by much. I missed it by 1/10 of a percent, actually. Not 1%, but 1/10 of a percent, 0.001. That's the relative error. So, can I somehow, based on this information, entertain hope that my candidate for solution is also, let's say, comparably close to the actual solution? Is it possible the relative error of my solution, of my candidate, is just, let's say, 0.1%, or 2 perhaps, 0.2%? That's a good question. I actually know the solution of that system, and I can also do this. I can look at the difference between actual solution and my guess. That's the vector E, that's exactly this vector. And I do the same trick for each entry in this error vector. I divide it by the corresponding entry in the solution. So for each coordinate in the solution, I find the relative error of my guess, and I take the largest of them, which is 0.264. So the relative error of the solution calculated in this way is 200 times larger, more than 200 times larger, than the relative error of the residual, so to speak, okay? By how much I missed reaching the right-hand side. So here I observe the error of about 0.1%, but the actual error is 25%. So this shows us two things. First of all, that transforming information from residual to the error does not seem to work all that well, or let's say as well as we would hope. So there are some things happening that we should really investigate. So that's definitely one important takeaway from this example. And the second takeaway is that we don't really have tools for it yet. What I did was, let's say, natural, intuitively. I was handling each entry in my solution, each entry in my error vector, and so on, separately, treating them like estimates of numbers, looking for relative errors and so on. But this is rather unwieldy. This is not very convenient for working with especially large systems, like million by million. I definitely do not want to look at a vector which has million entries and work with each of them separately. So it makes much more sense to work with these vectors as units, as a whole. I can just look at the vector R, residual vector, and ask how large it is, and compare it to the vector, to the magnitude of the vector, showing me the errors of my solution. And of course, we have some magnitude, the notion, which is the usual magnitude that we know from physics, for instance, or geometry. So when somebody gives me a vector, then of course the magnitude is naturally calculated as square root of summation of xi in absolute value squared. That's the usual magnitude of a vector. However, let's have a look at this example. Imagine that the residual vector is really large, let's say million by million. Okay, so n, the dimension of the space is 10 to the power 6. And this residual vector is 0.01, 0.01, and so on, 0.01. So I actually didn't make such a big mistake. Or this could be perhaps the error vector. That may be even better story, okay? So let me change it. Let's make it into the error vector. So when I look at it, I would think, okay, perhaps the error is not so large because at each unknown, essentially, because these are really the unknowns in my system. For each unknown, I've made a mistake of 0.01. So I'm mildly optimistic, perhaps. But if I take the usual magnitude of this vector, I have to square 0.01, sum them up a million times, and they take square root. And it's not really hard to calculate it. So I'm actually taking square root of a million times 0.01 squared. And then when you take square root, you get 10. Which is a number that is much larger, significantly larger than the individual entries which show errors of my variables, of my unknowns. Now, if the magnitude was 10 to 9, things would get even worse. In general, if you have a vector like that of dimension n, then the magnitude is square root of n times 0.01. This goes to infinity when you work with larger systems. But still, the message should be the same for systems of all sizes. This is the, let's say, reliability, in a way, of my guess for the solution. So we need a different way of measuring vectors. This is not a bad way, but it's not exactly appropriate for our task. What I would really prefer is this. When I look at a vector like that, I would prefer to ask which is the largest entry here. And that's exactly what I did over there in my calculations. So what I want to say is I want to say that the magnitude of some vector, and it's a different, new kind of magnitude. I will introduce some notation soon. So the magnitude or the size of such a vector will be the largest entry, maximum of xi in absolute value. And the maximum is taken through all possible i's. Now, that's a reasonable way of assessing impact of a vector, of an error, which has more dimensions, multi-dimensional error. Would it work? Would this way of measuring vectors be useful? Could I manipulate it in some reasonable mathematical way? And this brings us to an interesting idea that we can actually measure magnitudes in different ways. And when you are measuring magnitudes of vectors, when you have a vector, geometrical vector, you are actually also talking about measuring distances between points. So does it make sense to measure distances in different ways? And the answer is, of course it does. For instance, imagine that you are a taxi driver and you are supposed to go from here to here. Okay? However, the problem is that there is a regular rectangular grid of streets, and of course, unless your car has wings, you cannot really get from here to here in the usual Euclidean way. This is the Euclidean norm. That's how it's called, Euclidean distance. So you cannot use the usual magnitude of the vector that we know from geometry. You have to go this way. So what is the distance that you are covering? Well, it's actually the first coordinate of the distance as a vector plus the second coordinate. So when you are a taxi driver, you would actually think that a magnitude of a specific vector is a summation of the individual coordinates. That's how taxi drivers in a regular square city see distances. So that's a different way of measuring distance. Does it make sense? The answer is actually yes. There is a very general notion which covers all kinds of possible ways of measuring distances or ways of measuring sizes of vectors, magnitudes of vectors. It's something which is called norm. So let's make a little side trip to a totally different part of mathematics, and we will borrow some tools from there. Here is the first definition. I have a vector space. And we know from linear algebra that vector space, this could mean anything. Functions can form a vector space, polynomials can form a vector space, matrices form a vector space. So I simply have some objects which I want to measure. And the vector space assumption means that I also have a way of adding those objects and multiplying them by numbers. That's what I can do with them. Now, if I want to measure magnitude of these objects, it essentially means that each of these objects get a number assigned to it. So I'm talking about a function or a mapping, perhaps, which is what we can see over there on the right. There is a mapping denoted by triple bar notation. And this mapping takes vectors and changes them into numbers. Now, to call this mapping a norm, it has to be special. And there are 4 requirements which are required for a mapping to be called norm. The first requirement asks that all magnitudes defined in this way have to be non-negative. This makes sense. When you say that something has a negative magnitude or negative size, this sounds bad. So this is a reasonable assumption. The second requirement is that the only element which has magnitude 0 is the 0 itself. This is also very convenient. It makes sense in applications. The third assumption says that if you take an object, a vector, and scale it, let's say you enlarge it twice, then also the magnitude of this object should be enlarged twice, or 3 times, 4 times. Simply the notion of magnitude which you are considering should respect scaling, should work reasonably well with respect to scaling of objects. So again, that's a very natural requirement. The fourth requirement is so-called triangle inequality. Why is it called so? Let's draw a picture. I have 2 vectors, x and y, and I will be trying to add them. So how does it work? Well, we have one vector, x, and you connect the second one so that it follows, so that it continues in the way. And then when you connect like that, that's exactly x plus y. Now the triangle inequality says the following. You can get from the original place to the target place in one go. And that's on the left. And you ask how large it is, which means how distant these two guys are when you are going straight from one to another. And this cannot be larger compared to some detour that you take. So when you take a detour, it cannot shorten your journey. That's the meaning of triangle inequality. And if you decide to measure the space in some way, the world in some way, which is convenient for you, but you also need this way of measurement to be reasonable so that you can work with it, find some formulas for it, or simply you can live with such a world, you need triangle inequality. If you decide to measure the world in a different way, such that the triangle inequality does not work, then you get all kinds of weird behavior in it. And you definitely don't want that, especially if you are a physicist or whatever, mathematician. So when we are considering different ways of measuring vectors, which means of measuring objects, we always try to go for these four properties, and if we have them, we are happy, and this way of measuring vectors is called a norm. Okay? So there is a big theory about norms, and let me introduce some popular norms. The first popular norm is the usual Euclidean norm, the one that you know from geometry or physics. That one is very popular, and sometimes it is denoted with a subscript 2. The second interesting example is so-called max norm, which is this one, and we can see on the slide that the notation has little infinity here. That's how we recognize maximum norm. And it is a norm. One can prove that these four properties are okay, including the triangle inequality. And taxi driver norm, summation norm, is denoted by subscript 1. And it is also used in some applications. For numerical analysis, the maximum norm or the infinity norm is our favorite, definitely. But in the theory, we usually try to develop it in such a way that we don't care about the norm. We are trying to develop theory so that it works for all norms. That's the advantage of general mathematics, because you just develop one theory and people can use it in different settings. Okay? So I will try to work just with the general norm in our theoretical statements, and I will denote it using triple bar, like in the definition. And then the triple bar norm can be replaced by any other norm, any particular norm. Now, there are actually more norms, infinitely many norms, lots of crazy ideas. But there is one specific family which is, let's say, popular, and I didn't talk about it, so this is just in passing, we will not need it. But it's so-called p-norms. P-norms, they work like that. You sum up the pth power of the individual coordinates, and then you take the pth root. So that's one general family with parameter p, and if you want triangular inequality, p must be at least 1. Now, if p is 1, you get the sum norm, because you're just summing up. So you can see that this is a special case of this p family. If you put p equal to 2, you will get the Euclidean norm. Now the trick is, if you take a vector, a particular vector, concrete vector, and you send p to infinity in a limit, you get exactly the maximum. That's why there is this infinity here. This also fits with the p family of norms. So these are really very popular. Perhaps let me go a little bit on a tangent, because this is a very interesting field of mathematics. This is called functional analysis, and specifically perhaps Banach space theory. So this is a very nice mathematics. And let me talk a little bit about it, because some of it will perhaps come useful. When you decide on measuring distances, you are essentially specifying how you perceive the world. This is very interesting, because the way you measure distances actually gives shape to your world. For instance, let me show you something. In physics, we measure distances in many ways, but one possible way is by asking how far light goes in a specific time. And this will determine a circle or a ball in 3D, in physics, or in geometry. We talk about unit ball or unit sphere. So if you decide to measure distances in the usual way, the Euclidean way, square root of xi squared, summation, then everything which has distance 1 from you when you are sitting here forms a circle. So this is the unit sphere in a world if you are measuring it in the usual Euclidean way. So that's how we perceive circles. But if you somehow get transformed into the world, which is measured fundamentally, physically, by the maximum norm, then you are sitting here and you are asking, okay, what are the places which have distance 1 from me? And the interesting answer is that these places look like this. These points have distance 1 from the origin, and therefore this shape is the unit sphere, and you fill it in, that's the unit ball, okay? Ball of radius 1. So that's in the world with infinity norm. On the other hand, if you decide to measure distances using the taxi driver norm, so this is how taxi drivers actually perceive the world. If you ask taxi driver, sitting here, what places in the world have distance 1, he would tell you these places. So in the world of taxi drivers, unit circle looks like this. One is here. So by changing the norm, the way you measure distances, you are actually changing the geometry, the shape of the world as you can see it, and everything works differently when you change the norm. This is interesting. Now, when you are changing p in the p norm, you start from 1, you go to 2, and then you go all the way to infinity. The shape actually changes in a continuous way, like in the morphing software. So you start with this shape, and you can actually see that it has corners. But when you start increasing p, these sides, they start getting like that, and you don't get corners here. These are round now. And you keep increasing p until you hit 2, when you get a nice sphere, and then you keep increasing p, and those sides are actually bulging out. And you still have a nice oblong shape, smooth shape, until you hit infinity with p in limit, and you get new corners here on the outside. So when it comes to the family of p norms, the 1 norm and the infinity norm, they are special, and they are actually quite bad because of that, because they have sharp corners. So the balls of these two spaces have corners. That's how you would say it in functional analysis. Very interesting. Another interesting thing is that when you decide on measuring distances, you are actually also deciding on how things work in sequences. You are deciding on the limit notion. Because when you have a sequence of vectors, and you ask, do they go to some other vector? Good question. And the answer is, well, you simply look at their distance. But how do you measure distance? You measure it with respect to some norm. And if the distance goes to 0, then you say that this sequence of vectors goes to this vector. So depending on the norm that you adopt in your world, you get different notions of convergence. Here is an interesting thing. When you are in a specific space, R to n, then the norms may be different, but all norms are comparable in the sense that you can find inequalities comparing them with some constants. For instance, in this world, R to n, the infinity norm is always the smallest possible norm of a specific vector. The 2 norm is larger, and the 1 norm is the largest possible of the p norms. However, the 1 norm, the taxi driver norm, can be bounded from above by n times the infinity norm, which is interesting. And you can try it, you can play with a vector which has 1s everywhere, and you can see that it's 1 norm, which is the sum norm is n, and the infinity norm is equal to 1. So that's a vector which nicely shows the extremes between the 1 norm and the maximum norm. But there is comparison going both ways. And therefore, if you have a specific space of a specific dimension, all the convergences actually come up to the same notion. So when you have a sequence and you ask, does it go to a specific vector? Then the answer, yes or no, does not depend on the norm. Only the speed of convergence does. But the convergence itself is always determined, for instance, by this nice norm. You don't have to worry about it. And in turn, convergence in Rn is essentially what you would expect it to be. You just look at individual coordinates and you ask, do they go to this coordinate and this coordinate? You do it coordinate-wise. Okay? So that's another aspect, and we will actually need it later on and also in the following follow-up lecture. So this will actually come useful. Anyway, now we know that we can measure vectors in different ways. And of course, as I said, in numerical analysis, we definitely prefer the maximum norm because it just looks at a vector and tells us, let's say, intuitively the correct information. So let's revisit our example. The one which looked good at the first sight, but in reality, the candidate for a solution didn't work out really well. And we actually see the numbers here. On the top, we see 0.1%. That was a number which are obtained by doing some calculations by hand. They were not scientific. They were sort of like, let's say, intuitive. And here we can see the error of the solution or the candidate for the solution. And I will try the same thing, but with norms. So I will take the residual and look at the norm of the residual. And to see relative importance, I will divide it by the norm of the right-hand side. So I'm no longer comparing individually entries and vectors, but I look at vectors as units. And I look at the magnitude of the residual and divide it by the magnitude of the right-hand side vector. And I get number which is 0.0006, which is actually even smaller than I had before, because before it was 0.001 when I was working with each entry separately. In the second row, in the middle row, I can see the relative error of the solution, again handled by looking at the error as a vector and asking about the magnitude using the maximum norm, and I divide it by the norm of the actual solution. And it comes to be 0.066 and so on. And again, I look at the ratio and I see that the ratio is 100. So when I look at this information through the lens of norm, I ask for the norm of the residual and I ask myself, okay, the residual has a reasonably small relative norm. Does it mean that the error also has a relatively small norm? And the answer is no, because the norm of the error is 100 times larger than the norm of the residual, taken as a relative, because that's the important thing. We always work with relative error. So this confirms my suspicion that the information about residual and the information about error, they are not directly comparable easily. And it also shows that I can work with vectors and get meaningful information out of it, because the message which I'm getting is very similar to the message which I was getting by those intuitive calculations. The advantage of the norm approach is that we can develop some theory and some tools which will allow us to sort of make sense of the information and perhaps find some ways of doing things. Okay? So definitely, norms are a very, very useful tool. Okay, let's go back to theory. We learned how to measure vectors. So I look at this equality or this equality. Okay, here. And I can measure the magnitude of the residual in some norm. Again, I'm using triple norm. I will be using it later, this with maximum norm, but perhaps also somebody prefers a different norm. So I will just take some norm of a vector. I can measure the magnitude, the norm of the residual. And I'm asking, can I get some information about the norm of the error of my solution? And I can apply norm to this equality, for instance, and I find that the norm of the error is norm of A inverse times residual. Can I get somehow farther? Because I know the norm of the residual, I can calculate it easily. But here the norm actually does not apply to residual, it applies only to this whole group. Can I somehow split it? Well, let's see how it would work if the dimension was 1. 1 by 1 matrix is just a number. So the error would be number inverse times R, and I can simply take absolute value and apply it to each term. And voila, knowing the magnitude of R as a number, I know the magnitude of the error. That would be nice. Can I split it like that? Can I take this product and split it into two parts? Well, I can apply magnitude to the residual. No problem there. But here, A inverse, that's a matrix. And so far, we only talked about measuring vectors. So if I want to somehow work out this equality, to make some sense of it, I need to be able to also measure matrices. And this is something new, because this is not typically done. Measuring matrices, that's an unknown topic, essentially for people who went through high school and perhaps 1 or 2 years of university. This is not something typical. Everybody knows Euclidean norm, but when you say norm of a matrix, people usually say, oh, what is it? So let's have a look at it. First, definition. Of course, if I want to measure matrices in a reasonable way, I want all the 4 properties to be satisfied. So there should be triangle inequality, it should handle scaling well, and so on. So I want any norm of a matrix to be a norm, naturally. But matrices also can be multiplied, which is something that normal vector objects do not do. For instance, I cannot just take 2 vectors and somehow multiply them to get another vector. In general, this does not work. But matrices are special. And therefore, we also introduce a special notion which is called matrix norm. A matrix norm is a usual norm for properties, but there is an extra property which tells us that the matrix norm can actually work well with matrix multiplication. Now, you may think, inspired by this equality here, when I apply absolute value, you may think that it would be actually nice if the norm of A times B was equal to norm of A times norm of B. That would definitely be nice, but unfortunately this requirement is too strict. And if we insisted on such a requirement, then majority of practical matrix norms would no longer be matrix norms. This is simply too strict. This would rule out most candidates. Really unreasonable assumption. So when we add inequality, suddenly many good candidates become matrix norms because they work like that. And moreover, as we will see, this inequality goes in the right direction. So that's exactly how we want it. So now we know what we are looking for. We are looking for some way of measuring matrices which satisfies the 4 properties, and moreover, it also works well with multiplication. Now, did we measure matrices before? Yes. We talked about the determinant of matrix. Okay, determinant of A. Does it satisfy the properties? The first property was that the number must be always non-negative. Well, out of luck. Determinant can be negative. So why don't we take absolute value? Could absolute value of determinant be a measure of magnitude for a matrix? And the answer is no. Why not? Because the second property said a norm of an object can be 0 only if this object itself is 0. So of course, if you take a 0 matrix, then the determinant is 0. In one direction it works, but it doesn't work in the other direction. For instance, when you take a matrix like that, this matrix is not a 0 matrix, definitely not. But when you calculate the determinant, you get 0. So this spoils the idea that determinant somehow could lead to a magnitude for matrices. No, we cannot measure matrices in the way of determinant. So how do we measure matrices? That's a good question. Well, one can look at these examples here at the popular norms and think, okay, why don't I take inspiration here? But it turns out that there are troubles. So in the end, people ended up with something different. Let's have a look at it. Some popular matrix norms. And let's make some room. Okay, let's have a look at it. I have a matrix here which is n by n. And the first column is ones, and all the other entries are 0. And let's say that I'm interested in the first norm, which is called infinity norm or R norm, and on the right we can see that it's called row sum norm. So how does it go? We are summing up entries in the matrix, but you can see that the summation runs through j's, and j is the column index. So we are changing columns and summing up. For which I? For a specific I. We choose a row and we sum up everything in this row. That's why it's called a row sum norm. So I sum up the first row and I get 1, and I sum up the second row and I get 1, and so on. Each row gives me summation 1, but that's of course a special example. And then I should take maximum of these outcomes. So when I take the largest, I get that the infinity norm of this matrix, let's call it A, is just 1. So that's the row sum norm. The column sum norm does exactly the same business, but notice that I'm summing up with respect to I, which means with respect to the row index. I'm going down when I'm summing up. So I sum up all the columns, and they are almost all equal to 0, those summations, but the first summation is n. And then I take the largest, and I find that the 1 norm is equal to n. Now, one thing that we can notice is that I'm using a notation which is familiar. It's very similar to the one which we had for vectors, but actually I'm using different calculations. So this is a little bit strange. Finally, the last norm looks okay. Now we have something familiar. We take all the entries in the matrix, square them, sum them up, and they take square root. That's something which looks like the usual norm of a vector, and now we are applying it to matrices. Wonderful. What is the norm, this kind of norm, of the matrix A? Well, I square everything, then I sum it up, and I get n, and then I get square root of n, and I'm done. Okay, now, here is a surprise. The formula is familiar, but the notation not. This is not called A2 norm, but AF norm, so things are really strange. In the first two examples, the notation matches the one that we have for vectors, but not the formula. Here the formula matches the one for vectors, but not the notation. Things are really strange for matrices, and this is just the beginning. Let's imagine that I would take this matrix and transpose it. Well, if I transpose it, then the rows and columns, they just change their places, and therefore, when I look at the transposed matrix, the row norm, and I remember it really nicely because infinity is sort of like flat, horizontal, like rows. So the row norm of the transposed matrix means I'm looking at columns of the original matrix, and it becomes n. Yes, they interchange. And likewise, when I look at the transposed matrix at its column norm, and number 1 is sort of like vertical, narrow and tall. So it's like a column. So when I'm looking for columns in a transposed matrix, it means I'm looking for rows in the original one. And the norm becomes 1. So just by transposing matrix, the roles of infinity and 1 norms, they change, they flip. And this tells me that there is no hope of some hierarchy, like we had for norms of vectors. So I cannot really say that one norm will be smaller than the other always, something like that. Never works. What does work is that they are comparable using inequalities. Again, I could find inequalities which compare chosen two norms. There will be some inequality with some constants. This can be done. So I have convergence for matrices, which is based on norms, matrix norms. But again, for matrices, convergence actually works by individual entries. When you have a sequence of matrices and you want to know the limit, you just make a limit of each entry in the sequence, and you get a new matrix. Okay? So things work really, let's say, intuitively, reasonably. Another difference compared to the world of vectors is that for matrices, there is no default norm. When you work with vectors and you say norm, then people typically expect you to use the Euclidean norm because it works well in most situations, and it works really well in many situations. And only occasionally, when we have some specific need, we pass to some other norm. Okay? But in general, the Euclidean norm is a good default. There is nothing like that for matrices. Every matrix norm is special, that it has a, let's say, narrow field of action where it is really perfect. And in other situations, it's not really good. So there is no default norm for matrices. It doesn't make sense to say, let's take the D norm of a matrix, because nobody would know which norm we are talking about. However, this does not mean that you cannot say something nice about matrix norms. There is a theory where they prove all kinds of properties. And let me show you one example because we will need it. I claim that if you pick some way of measuring matrices, some matrix norm, then the norm of the unit matrix must always be greater than or equal to 1. Or to put it another way, it's not possible to invent a matrix norm so that the unit matrix will be smaller than 1. That's another way to put it. How do I prove it? The answer is easily on a few lines. Let's start with this identity. We know that unit matrix, when it multiplies another matrix, preserves the matrix. Here we go. Very easy. Now, because these are two equal matrices, then they also have to have the same magnitude. So if I add the mark for norm to the matrix on the left, I should get the same number as on the right-hand side. Here I can use the inequality which we had for matrix norms, the one which the fifth requirement. And the fifth requirement said that I can split this product into a product of norms, like that. But I have to pay for it by this inequality. And finally, we recall that because the identity matrix is definitely not the zero matrix, then the norm of it simply cannot be 0. And therefore we can divide on both sides. And moreover, it's positive. That's another of the properties. It cannot be negative. And therefore we preserve the direction of the inequality. And when we divide, we get exactly the inequality that we're looking for. Okay, so that's the end of the proof. And we feel much better because finally we had some nice proof in this lecture. Lecture without a proof just doesn't feel right. Okay, so that was just one interesting example that we can actually do something with the matrix norms. We can do some theory about them. Okay, now let's go back to our initial problem. I have some candidate for a solution of a system of equations. I look at the error and I ask how large it is. Now, I'm going to use this identity. So I put A inverse and the residual here, and I would like to split it. If I split it, I can apply vector norm here, and I can apply matrix norm here, some matrix norm. But how do I know that they will work together well, that they will really make this expression equal to the new expression? Well, of course I don't, because if I choose some vector norm here and some matrix norm here, there is no guarantee that I could connect them in algebraic identity like that. So what we need to do now is to look at our possible vector norms and matrix norm and find pairs that really work well together. There is a special name for it. Here we go. We have a norm for vectors and some matrix norm for matrices, and I have to use different notation to distinguish between a norm for vectors and a norm for matrices. And I say that they are compatible if I can take a product like the one I have here and multiply it out with norms. And again, I would prefer to have equality there, but it's impossible. If I raise my bar so high that I want to have equality, then almost no norm will crawl over it. This would be really suicidal, essentially, to ask for that much. So I'm going to lower my expectations. I just ask for inequality. And again, it's inequality which goes in the right way. Now, if I find a pair, a matching pair of a vector norm and a matrix norm, then I would be able to get this formula. And this looks rather interesting because it tells me that if I know my residual, if I know how large it is, and if I know the norm of my inverse matrix, then I find an upper bound for the norm of the error. An upper bound, that's exactly what I want because I want the error to go down. I want to keep it down. I want it small. Okay? So this inequality is finally something that I have been aiming for. Okay. Where do I get the matching pairs? The answer is, well, actually, there are many of them. But this actually, the fact that there are many of them, makes it more difficult for us to work with them. So it's actually better to restrict our freedom of choice and look at pairs which are sort of made for each other, because it turns out that there is such a thing, that it's possible for every matrix norm to find a vector norm which is perfect fit for it, and vice versa. How will it work? Typically, we actually start with a vector norm. So we have vectors, and we have a way of measuring them. And we would like to introduce some way of measuring matrices, which is a perfect fit for this norm with respect to this multiplication out. Okay? Now, another thing, and we will get to it soon, is that we want our norms to be as small as possible. So for a given matrix, I'm looking for a number which is smallest possible, and at the same time this number should provide me with the following inequality. Here is this number, and here is this vector. So I'm looking for the smallest possible number so that this works for every vector. And I can take this number and move it to the left. So I'm actually looking for the smallest number which satisfies this inequality. And a little logical reasoning, how do I find the smallest number which satisfies this inequality for all vectors x? Well, I simply look at these numbers, how large they are, and the largest of them I pick for this number. Okay? Because this is a set of some numbers, and I want something which binds them from above. I'm looking for upper bound. So I'm simply looking at these numbers. They look somehow on the real line. Here is 0. These numbers are positive, or perhaps 0 also. So there is a bunch of possible ratios, and I'm looking for the smallest number which is above them. So the smallest number above them is actually the largest of these numbers. Okay? So by taking the largest number, I am getting my candidate for the norm of A, for the matrix norm of A. And I could do this for every matrix. For every matrix, I could look at these numbers, and based on them, I could determine some parameter of A, which I would call a matrix norm, but I am not sure that it's a matrix norm. I mean, the idea is neat, but it may happen that in this way I build something which is not a norm. That would be very bad. But fortunately, this does not happen. So here is an interesting theorem. So it has two parts. Part number one is exactly what I've been talking about here. If I take a vector norm, then I can define a specific mapping for matrices, and this mapping works by simply looking at the ratios. Now, there is no guarantee that there will be a maximum which is attained, so I have to ask for supremum. I look at supremum, and the number which I get, that will be the norm for the matrix. I am not calling it a norm yet, I'm just saying it's a mapping. But then there comes the sentence, the statement, which says that in this way we obtain a norm, and it is a norm compatible with the vector norm. So they are really a good fit. They are perfect fit. And this matrix norm is called matrix norm generated by the original vector norm. So vector norm generates matrix norm. Now, part two of this theorem tells us that this also works the other way around. If you know how to measure matrices, you can measure vectors by turning them into a matrix. Using a trick which is very similar to this one. You just put your vector as the first column, fill the rest with zeros, and ask, how large is it? And you get a vector norm. And again, these two will be perfect fit for themselves. So if you start with a vector norm, and you use this trick to get the matrix norm, and then you apply the second part of the theorem to the matrix norm to get back to the vector norm, you actually do get back to this original norm. It's a cycle. So they are really perfect fit as seen from both sides, from the sides of the vector, from the side of the matrix. They really look perfectly made for each other. So these induced norms, these are perfect pairings. That's what we want to use in applications. Now, good questions. Okay, if I take the infinity norm for vectors, because that's what we prefer in analysis, in numerical analysis, in numerical calculations. What is the induced norm for matrices? And the answer is the infinity norm for matrices. Now you can see justification for the notation. This is actually the row sum norm, when they are summing up rows and taking maximum. So this norm is a perfect fit for the maximum norm for vectors. Now, you are probably not going to be surprised when I tell you, when you take the sum norm for vectors, that's the taxi driver distance, then the induced norm for matrices is the column norm. Okay. What happens if you take the Euclidean norm? And the answer is you get a specific norm, which is called, not surprisingly, A2 norm. And it's so complicated to find it that it's not used in numerical analysis. It's used in theory because it's a perfect fit for the Euclidean norm. But in applications, this is really bad. You would need to do really, really serious calculations to actually get the 2 norm. So we don't use it. We don't want it, definitely. Okay. How about the Frobenius norm, which was here? That's the norm which is given by the natural formula, if you remember. Okay, let me go back. The Frobenius norm simply takes all the entries in the matrix, squares them, sums them up, takes square root. That's the Frobenius norm. So, what kind of vector norm has the Frobenius norm as its friend? And the answer is there is no such norm. And this is really bad for the Frobenius norm. It's not induced by any vector norm, and therefore it does not fit into our theory. So we don't want this one either. But sometimes people use it in applications because in some contexts it actually provides useful information. But we will not definitely be using it here because it's not good for us. It's not friendly with any vector norm. It's not induced by a vector form. So essentially, again, we are left with this one as the natural candidate. Now, before we move on, let's make one more observation. The way in which we defined induced norms, it has another interesting interpretation. We know from linear algebra that every matrix actually defines a transformation. It takes a vector and moves it into A times this vector. So we have a space of vectors, and the matrix A, through multiplication, changes them into other vectors. Now, typically, some of these vectors, when they are sent over, they change orientation and they change magnitude, and we are not really interested in the case when they are getting smaller. This is no problem. But what we sometimes don't really like is when vectors are getting too large under such transformation. So what is the change of magnitude of vectors? What is the largest possible case, the one which we want to keep small, essentially? So in a way, we are asking, what is the measure of deformation? Because here, those vectors, they may determine some shape. For instance, when you have 3 vectors, they sort of define a shape like that. And after I move them over, they suddenly define a totally new shape. It's a triangle which changed the shape and also the size. So when I'm talking about deformation, I'm talking about deformation of objects through this mapping. Now, how does it work? Well, I look at the image of a vector, and I'm measuring distances in some way in this world. And I compare it with the original vector. And I'm asking, is there some constant which would tell me that there is an upper bound on the deformation? Or what is the largest deformation which is happening when I'm using A as a transformation? Now, when we compare it with the definition, I'm actually asking the same question, just in different words. So this number is actually the induced norm of A. So another way to interpret the induced norm is this. I have a vector space of vectors, and I decided to measure distances and to measure the geometry using some vector norm. And then I have a matrix which is deforming this world. and I'm asking what is the worst deformation that can happen. And the induced norm, the induced matrix norm, tells me exactly what is the worst case deformation. And this brings me to another linear algebra topic. When you have a matrix, you also have eigenvalues and eigenvectors. And with a bit of luck, those eigenvectors, they will form orthonormal basis or orthogonal basis. Let's not be too greedy. So you have a basis of your initial space, and when you move it using transformation determined by A, these eigenvectors, they of course deform, but they have to have the same orientation now. The only thing which changes, or the same direction, orientation may flip. The magnitude changes according to the eigenvalues. So the eigenvalues are actually also a measure of deformation, because they tell me how many times do these basic vectors, the eigenvectors, change their magnitude, and the worst deformation is given by the largest eigenvalue. So the largest eigenvalue tells me similar information as a matrix norm, and there is a name for it. When we have matrix A, we can look at the magnitude of the largest possible eigenvalue. We also, of course, include the complex eigenvalues in our list. And the largest eigenvalue is called spectral radius, rho. Interesting question. What does the spectral radius have to do with matrix norms? Well, first of all, unfortunately, it's not a norm. If it were a norm, it would help us a lot, but it's not. And again, the reason is that it does not recognize zero matrices. If you take this matrix, then the spectral radius is actually equal to 0 because the eigenvalues are 0 and 0. There is a double eigenvalue. So this shows that, unfortunately, spectral radius does not satisfy the conditions for the norm. And yet, there is a very close connection. We will soon see that it will be in our interest to make the norm as small as possible. So imagine the following situation. This is the positive real line. Now, I have a matrix, and I want to find its magnitude, but I'm not really particularly interested in any particular vector norm. So I'm trying different vector norms. I take one vector norm and look at the induced matrix norm, and it's this one. I try different vector norm. I look at the induced matrix norm of A, and I get this number, and this, and this, and this. And remember, I'm trying to get small numbers, so I'm trying to go as low as possible. And it turns out that there is a bound below which I cannot go, and this bound is exactly the spectral radius, in other words, the largest eigenvalue. Let me state it as a theorem. This theorem has two parts. The first part is that the norm, induced matrix norm, can never be smaller than the spectral radius. And this is actually easy to prove. Let me show you another proof here. So it's the second proper proof for today. Wonderful, good lecture. Okay. I have a matrix, and I assume that the largest eigenvalue is called lambda. Okay, so lambda is the largest eigenvalue. And it has eigenvector v. What does it mean? Well, it means that AV is lambda v. Now I'm going to apply a vector norm to this. So I get vector norm of AV is equal to vector norm lambda v. Now on the left, I'm going to introduce the induced matrix norm applied to A, and I have to put inequality here, so there will be the norm of A, the induced one, times the norm of V, and on the right, property number 3, whatever, for any norm is that it works well with scaling. And here the vector is scaled by lambda, so also the magnitude of it must be scaled by lambda in absolute value. Okay, V is an eigenvector. Because it's eigenvector, it cannot be 0. So the norm cannot be 0. I can factor out like that. I can cancel. On the left, I have my induced matrix norm. And on the right, I have the largest eigenvalue, which is the spectral radius. Happy end. Very nice. Okay. What's more difficult, and significantly more, is the second statement that you can actually get arbitrarily close to spectral radius with matrix norms, which is a very nice theoretical result, very strong, but not very practical because we don't know which norms to use. And typically those norms will be rather unpleasant to work with. So in the end, we resign ourselves to work with the infinity norm, essentially, or sometimes the other norms are also used, but not much. This is the most frequently used norm in numerical analysis. And we simply know that very often it's not optimal. It's very far from the best case, which is achievable, which is the spectral radius. Finding spectral radius is also not easy, although it's very important, and we will see it in the next lecture. It will be really prominent there. So I wanted to introduce it now to show the connection, and it will shine in the next lecture. But for now, we will close this introduction, this visit to other parts of mathematics, because this was functional analysis with matrix norms and norms, some linear algebra, things like that. But we only really needed a language, some tools which will allow us to look at the magnitude of vectors of matrices, put information together. So now we are ready. Let's erase it and start talking about errors. Okay, finally, we have a system of linear equations. We found a solution, perhaps. We found a candidate for the solution. We want to know the error of this approximation of our solution. We found a residual, and we know that the residual and the error are connected in two ways. Let's have a look at it this way. I'm interested in the magnitude of the error, so I choose some vector norm, typically infinity norm, but let's not restrict ourselves. What is the infinity norm of my error? Well, here I can apply induced matrix norm to the inverse matrix and multiplied by the vector norm of the residual. And this tells me how the error of reaching the right-hand side is transformed into the error of my solution. But this is an absolute error. And we know that we don't really get much information from that. We want to see the relative error. So the relative error of my solution, and that's a number now, not a vector anymore, is the magnitude of the absolute error divided by the magnitude of the correct answer. And we have a nice inequality which allows us to replace the error, the absolute error, with this number. However, what we don't really like is the presence of the actual solution here because we don't know it. This is really bad. So what we do is this. The actual solution must satisfy the original equation. And therefore, well, here, ax0 must be exactly equal to b. Now, I can apply, again, norm here, split it, and so on, and I get the following inequality. The norm of the right-hand side is less than or equal the induced norm of A, of the matrix A, times the vector norm of the actual solution. And from this, I can actually derive estimate for the norm of the solution. Let's see. The norm of the solution is greater than or equal to 1 over the induced norm of the matrix times the norm of the right-hand side. Now, unfortunately, this goes in the other direction, in the opposite direction compared to the inequality here, but fortunately we actually need it. Why? Because we are replacing in the denominator. The right-hand side here should be larger than the left-hand side. If I want this ratio, this fraction, to get larger, I have to make the denominator smaller. So I replace this denominator with something which is smaller and everything fits. So there will be 1 over norm of A the induced norm, times the norm of B. Let's rewrite it. The relative error of my solution is bounded by the induced norm of matrix A times the induced norm of the inverse. And now there is the norm of residual divided by the norm of B. Now the residual tells me by how much I failed to achieve the right-hand side B. So this makes sense to interpret this as a relative failure of my purpose. I can call it, with a little bit of stretch, epsilon B. Epsilon error in achieving B. And we have a very nice inequality which connects information which I have, because this is the norm of residual, norm of right-hand side. I can get these easily. Some, let's say, description of the behavior of the matrix, the norm of A, the norm of A inverse, and this gives me upper bound for the relative error of the solution. So this constant here, this is very important, and this is called the condition number, and as you can see, it depends on the chosen norm. So let me put it here. But usually people are too lazy. So when I wrote the definition here, I wrote it the usual way. So the conditional number of some matrix is just the norm of A times norm of A inverse. But which norm? That's the right question. So we have to say which norm we are using, and then it makes sense to talk about the condition number. And we can see over here that when we find our candidate for the solution, we find the residual, and if we get lucky, we find that the residual is small. So also the relative error here will be small. Very small number, very small residual divided by the magnitude of right-hand side, very small number. And if also the condition number is small, then our solution is good enough. If the condition number is large, then it could happen that our solution is bad, which was actually the example that we had there. Let's have a look at it. If you recall, we had a 4x4 system and a candidate for solution. And I looked at the the relative error of the right-hand side, and it was 0.0006, and so on. That's exactly this number. And then I determined the relative error of the solution, which was 0.066, which was 100 times larger. So the conclusion is that our matrix must have condition number at least 100, perhaps even more, but it must be at least 100. Let's ask about it. That's my question over here. See, I'm asking here for a condition number. And it's with respect to infinity norm. Now we understand finally what the notation says here in those calculations. So the condition number of our matrix is 270, which is a lot. This means that the matrix is not really very friendly. We can expect all kinds of troubles when we are working with this matrix. So matrices essentially, roughly and broadly, fall into two categories. There are matrices which are called badly conditioned matrices, and these matrices can be recognized by a huge condition number. What does it mean, huge? The answer is, I don't know, nobody knows. It depends, because for larger matrices, you get naturally larger condition numbers. That's how it goes. So for a 2x2 matrix, condition number 10 may be quite bad, but for a matrix 1000 by 1000, condition number 10 is actually really good. So there is no fixed boundary between good and bad matrices, well-conditioned matrices and badly conditioned matrices. These are sort of like fuzzy categories. We are thinking more about the extremes. So really huge numbers, they are bad, whatever. What is the good case? The good case is when condition number is close to 1, because 1 is the minimum that you can get. How do we know? Well, easy. Let's have a look at this. That's the condition number of a specific matrix with respect to a specific norm. Now, that's multiplication, and we can use inequality, which is true for matrix norms. Usually we use it in the other direction, so now we used it in this direction. Now A times A inverse is simply the identity matrix, and we proved 10-15 minutes ago that this is more or equal to 1. So the condition number for any norm cannot be smaller than 1. But if it's close to 1, we are really happy. Anyway, let's close this whole section. we were interested in how, knowing residual, we can actually learn something about the quality of our solution. And this is the answer, and it's quite important, so let's put it up. Let's make it official. Here we have a statement which essentially just copies this inequality and then makes a shortcut which looks like this, I believe. Yeah, but I'm just using the condition number there because we already have the definition. So this closes the chapter, how does residual tell us something about the reliability of our result? But there is actually more to condition number. So let's erase the blackboard and start from a different angle. Okay, here we go. We have a system of linear equations, and this system has a solution. Now, we want to find it, so we use a method, and it can be expected that what we find is actually not the solution, but some other vector. And there is an interesting point of view. I can see it like that. What I found is actually a correct solution to incorrect system, because as I was finding the solution, I was perhaps making some modifications. Perhaps I used elimination, because when you do elimination, you're actually modifying the system. So what we really do have is the original system, which I will denote like that. And for the original system, we have equality A naught x naught is equal to B naught. And then we have some other system, which has matrix A and right-hand side B, and the vector x is an actual solution of this modified system. Now, this is typical for elimination, because in elimination you are making some small errors, but I actually don't want to talk about elimination, because this is simply a general problem. You have a precise and imprecise solution, and for the imprecise solution, this can be often traced back to a specific system of equations for which this is an actual solution. Good question is, if these two are really close, the matrix and the right-hand side, are also the solutions really close? Because let's go back to elimination. When we do elimination, we are using partial pivoting to keep the changes as small as possible. So is it worth it if I use partial pivoting and the elimination is really almost precise? Can I hope that also my solution will be almost precise? That's a good question. Let's make a little analysis. To make it easier, I will start by assuming, it's not a very good assumption, but okay, that we did not do any really errors when eliminating A just with the right-hand side, okay? It will make our lives much easier. So the matrix A naught is preserved, and I only changed the right-hand side. Now, what is the advantage? The advantage is that I can now subtract these two equations. And when I subtract them, then on the right, I can see the error of the right-hand side. What do I see on the left? When I subtract the second equation from the first one, I can factor out the common matrix. That's why I wanted it to be the same. And after I factor it out, I will get x naught minus x, which is the error of my solution. And this is exactly the type of equation we were handling a short while ago. The only difference is that there was the residual here on the right. Okay? So I can repeat the calculations, and after I repeat them, I get that the relative error of the solution is bounded by the condition number of my matrix, and I'm using some specific norm, and then the relative error of the right-hand side. And now it really is a relative error of right-hand side because I modified it. Okay? So the calculations are exactly the same as before, and I get this interesting formula. This tells me that actually the condition number tells me something not about elimination, but about system as such, about sensitivity of the system to small changes in the right-hand side of the equation. So if I have a system and the matrix of the system is badly conditioned, then the system is extremely sensitive to small errors, and it doesn't matter whether you make those errors due to elimination or due to something else. It's simply extremely sensitive. Let's have a look. This is the official confirmation, and I hope it fits. It does. Now, let's talk a little bit about interpretation. If you remember, relative error tells us roughly how many digits we can trust in our answer or in some number. So here is essentially, in some way, encoded the number of digits that we can trust when we are manipulating the right-hand side. And here is the number of digits that we can trust when we look at the solution. And now it goes by powers of 10. If I multiply relative error by 10, I'm losing 1 digit of precision. If I multiply it by 100, and so on. So if I see this number as 10 to p, I'm losing p digits. This can be written using logarithms. So this is unofficial, but it does tell us something. So if I can trust this vector to a certain number of digits, k, then the answer, the solution, can be trusted to k minus logarithm, the decadal logarithm, of the condition number digits. Okay? So this is just out of curiosity to see interpretation. But what is more interesting is this next theorem, where we actually do consider the general situation. I'm not going to show the calculations here because they are, let's say, more difficult, significantly more difficult. Some tricks have to be done. And when you look at the answer, at the conclusion, you can see that it's not really pleasant because the solution is there and the actual solution is also there, the precise solution. This is not a very pleasant formula. But if you get lucky and the solution and the actual solution are not too far, you can imagine that the ratio is 1, just for the sake of interpretation. And then the formula actually says, on the right, you can see the relative error of the right-hand side plus the relative error of the matrix. So this in some way represents the relative error of the, let's say, elimination or whatever you did to the system. And this relative error of the system is multiplied by the condition number, and this then tells you the relative error of the solution, upper bound. It can be better, but you never know. So this is the story. Let's have a look at some experiments. I have here the familiar matrix 4x4, symmetric, and so on. We've seen it before. I have a right-hand side which is exactly the same as before. And now I have right-hand side with error, B error, which was changed. And when you compare the numbers, especially the second one is quite telling, we changed the right-hand side by 1%, by 1% only. Okay? So this epsilon b is 0.01, in other words. And then I solve the system for b, I solve it for b with error, and I compare errors, I look at the relative error of the solution of the modified system. Okay? So what I'm really looking at is this number. And we get number 0.8. This is really bad. If you remember, the condition number for the matrix 4x4 that we are playing with is 270. We can see it on the top. Okay? And this example shows that we are actually not fulfilling the full potential of this example because the error of the right-hand side is 1% and the condition number is 270. So we can get as much as 2.7 as the relative error of the solution, but we are getting just 0.8, which is not as bad as it could be, but still this is 80 times worse than the error in the right-hand side. So this 4x4 system is extremely sensitive to small changes because it is badly conditioned. Okay? Let's have a look at another example. What I did here, I took the original matrix. Let me scroll it a little bit so that you can see it. Okay. On the top, that's the familiar 4x4 matrix. It's symmetric, so it's really nice. And I changed it by 1%. Again, you can compare the numbers. Instead of 7, we can see 707. I added 1% of the original number, and so on. So each number was changed by only 1%. And then I left the right-hand side as it was, so it actually stayed the same. And I calculated exact solution of the original system, and then I calculated exact solution of the changed system with a small 1% error. And here what we can see is the relative error of this new solution of the change system, and it's 55. So this is 5,500 times worse than the change in the matrix. How is it possible if the condition number is just 250? Well, that's because, if you remember, in the formula, the relative error of the matrix is multiplied by the ratio, and this ratio is really huge as well here. So things can get really bad, and they did get bad. Now, for comparison, let's have a look at another matrix. And when you look at it, you can also see that it's symmetric. As I said, this is not really important, but I'm trying to show that matrix properties, and symmetry is a very nice property, do not really help here, okay? What we are talking about is independent of symmetry and things like that. So I have a matrix, and the condition number of this matrix is 7, which is close to 1. So I think I could call it well-conditioned matrix. I'm not quite sure where the well-conditioning ends, but this is not a bad matrix with condition number 7. So again, I make 1% change in the matrix. Here is the right-hand side. And now I'm going to solve the original system and the system with the error. And let's see how it influences the solution. And we can see that the solution, the erroneous solution, has 1% error. The original system had 1% error, and the solution also has 1% error. This is how we like it. If you make a little change to the little error in handling the system, the solution doesn't fly totally off. It stays reasonably close to the actual solution. This is what we like, and this is the well-conditioned system. There is an interesting geometric explanation of well-conditioned and badly conditioned matrices, and this sensitivity. So let's think of this example. A 2x2 system is something that people usually know quite well from high school. And one of the advantages of such a system is that we can draw it. And actually, when I was in high school, I learned how to solve such system geometrically. The first equation represents a straight line. The second equation represents another straight line, and we are looking for the intersection. Okay? Now let's imagine that I make a tiny error which is this large. And let's say that I make it in the right-hand side. What does it mean that I make error in the right-hand side? It means that I shift the line. I shift it by this much. So instead of this one, I have, let's say, this one. And instead of this one, I have, for instance, this one. Now, these are straight lines, okay? Okay, this one doesn't look straight, but we will pretend that it's straight. This is the actual solution, but because of my errors, I actually found this solution. Now, is the error of my solution comparable to the error? The answer is, I would say that yes. So this system, if it looks like this, would be well conditioned. Now, let's have a look at another system. I will try to place the first line closely or similarly to the previous example. Yeah, this looks good. Now let's have a look at the second one. Let's imagine that it goes like that. Here is the actual solution. And I'm going to make the same error as before, this large. So this line moves a little bit. And also this line moves a little bit. And the new solution is here. Where is the error of the solution? The answer is it's over here. Is it comparable to the error in my calculations? The answer is definitely not. I changed my system just by a little bit, and the solution totally flew off. And here you can see the difference. When a matrix is badly conditioned, it essentially means that in some way it represents planes or hyperplanes, whatever, that are almost parallel, because that's the really bad case, okay? So let's have a look back at our 4x4 system, the one which was bad. Where is it? Over here. Now we see it on the top. When I look at the first row and at the third row and compare them, I can see that the third row is almost precisely double of the first row. Almost. So it's exactly this case, just in 4 dimensions. Okay? And that's how I actually cooked up this matrix. I did it intentionally because I wanted something badly conditioned. And the fourth row is almost the same as the first row again. So there's actually two rows which are almost the same as the first one when it comes to direction. And that's why it's badly conditioned. And you can see that when you're looking for a solution and you are not doing it precisely, then it doesn't matter whether you use elimination or some other procedure. As soon as you make a little mistake for whatever reason, badly conditioned system will punish you. So these systems, badly conditioned systems, are simply bad because they're extremely sensitive to all methods, essentially. In the next lecture, we will introduce a totally different approach which can, in a way, handle cases like that. It can avoid this problem. But this is essentially, badly conditioned matrices are simply matrices where one has to be extremely, extremely careful. Let me show an example. Here I have a 2x2 matrix. Look at it. The first row, the second row, they are almost the same. So I'm really worrying very much about this matrix. This is really badly conditioned. I have a vector of right-hand sides, and now I make a tiny error in my matrix when I'm working with it. So the erroneous matrix has 3 coordinates which are the same 3 entries, and the fourth entry is 50.5. There is a 1% change. Okay? So I changed the matrix by 1%, which is negligible, one would say. But let's compare the solutions. The original system has solution 4, 2, and after making 1% change in the matrix, solution suddenly became 8, -6, which is a totally different vector, totally different solution. So you can see how a tiny change in a badly conditioned matrix can have catastrophic consequences, essentially. You can throw out the second solution because it has nothing to do with the original system. Totally useless work, although you didn't make I didn't make a very bad mistake, just a 1% error, and it totally screwed up my work. So badly conditioned matrices are really, really dangerous. It should be said that this is an inequality. It does not need to happen all the time that when you make a small change in your system, the solution just goes away. It depends on luck. Generally, when you have a badly conditioned matrix, it is usually bad in some sort of directions, in some directions, one can say, I guess. So, depending on the right-hand side, you can either explore this possibility and use it up and get a really bad solution, but sometimes you get lucky and your particular system is not that sensitive. So, let's play with it a little bit. I have here my familiar system. That's my 4x4 system, the one which we had before, and we know that it has condition number 270. So what I'm going to do now, I'm going to generate randomly right-hand sides and solve 2 systems, the original one and the one with little error, 1% error, and compare the solutions and see how it works. So for this random right-hand side, the error in the solution was 74, which means 7,000%. So the original 1% error got magnified 7,500 times. So this is really bad. So let's try it again. And this time it's 76, 23. So it's different. And okay, this is still really bad. But compared to the previous one, it seems okay. So you can see that the errors are actually changing within a specific range. The smallest so far was 23 and the largest 76. So it seems that the possibilities are quite limited, but sometimes, wow, suddenly we have 90. It really depends on luck. This matrix is rather small, so the variability is not very large, but when you try this for large matrices, you can get sometimes very small numbers, sometimes insanely huge numbers. This is almost 100, so it means 10,000 times magnification of error. This is really bad. So one can play with it and see what happens. I just wonder what is the smallest number which I can achieve. I didn't drop below 23, which is also really bad. This means error got magnified by 2,500, essentially. So yes, badly conditioned matrices are simply bad. However, in applications, how do you recognize badly conditioned matrices? You would have to find inverse matrix, and then you would have to find the norms of A and the inverse matrix and multiply them. The problem is, if the matrix is badly conditioned, then the inverse matrix most likely is totally wrong. So you cannot trust this number. The second problem is that finding inverse matrix requires 2n cubed operations, or 5/3 if you are doing it using the back substitution, if you are smart. So you don't want to do this. So the condition number is something that we actually very often do not know, but it's a useful notion to talk about things, and we can estimate whether it's bad or not by other tricks. Here is one popular trick. Let's say that somebody gives you a really huge system of equations. You try to solve it, and you get something. And you are asking, okay, should I trust it, or is it a badly conditioned system and I cannot trust it? That's a good question. So what you can try is this. If you solved this by elimination, then you can store it using LUP decomposition, and therefore it's no trouble to solve the system again, and you introduce a tiny error in B. Very tiny error because you have it under control. You introduced it yourself. And you get some other solution. And you compare them. And if you find that these two solutions are wildly different, then you know for sure that the system is badly conditioned, and you cannot trust this one either. And what happens when you have a badly conditioned system? Well, you have to try some other tricks. Definitely not elimination, things like that. Badly conditioned systems are a hard problem, and there are really sophisticated methods to deal with it. For instance, see the next lecture. So that's the end of today's lecture. We learned that matrices fall into, roughly speaking, two categories. And if the matrix is well conditioned, then you can happily eliminate with partial pivoting to keep the error down, and things are reasonably okay. But if you are unlucky and your system is badly conditioned, sometimes we talk about system, not matrix, but the system. If the system is badly conditioned, then you are in for some fun, and good luck. Similarly, we also saw it a little bit before unofficially, that also differential equations can be well or badly conditioned, and so on. This is a general notion in numerical analysis. But for matrices, for the systems, this notion of conditioning can be done really well, properly, mathematically. It can be supported by proofs, by formulas. So it was a good place to actually explore it. Okay, that's it for the theory. And next time we will explore a totally different way of solving systems of linear equations. And you will see why it is important and why it's useful. Okay, see you next time. Is that it? Probably, yes. Did I make something stupid? Did I say something stupid? I hope not. Okay. I will see. If I am not happy with it, I will talk again. Okay. Okay.